Hi, this is Nick Siefert, Research Mechanical Engineer for the Department of Energy. I work at the National Energy Technology Laboratory inside the Office of Research and Development. This is a practice for a talk that's going to be given at the 31st International Pittsburgh Coal Conference on October 9th, 2014. And the topic is on looking at using municipal solid waste gasification to provide the energy to retrofit a coal power plant. So what we're talking about is keeping the some existing equipment at a coal power plant, but change the feedstock from coal to municipal solid waste. Because what we're trying to avoid here is we're not going to just put the municipal solid waste right into the existing boiler or combustion unit. There's going to be a separate municipal solid waste gasifier producing hydrogen and CO2. We're going to separate the hydrogen from the CO2 and then send that hydrogen to be combusted, and then we're going to sequester the CO2. Okay, so why municipal solid waste? Some of the pros are, we can, as they say, kill multiple birds with one stone, right? We can reduce waste. We can, and by doing so, we can reduce the demand for land that's being used for waste disposal. And we can also reduce the environmental pollution that comes from landfills. In addition, we can actually generate electricity and receive tipping fees. So there's a lot of potential positives with using municipal solid waste as energy. Of course, there's a lot of negatives with municipal solid waste as well. It must be shredded and sorted and grinded, possibly dried. Its chemical composition is highly complex and variable. And by complex, I particularly mean that there's also a lot of heavy metals or tars or halogens that could be produced. Or if you combust it, there'd be dioxins that could be produced. So there's a lot of complexity with municipal solid waste. Of course, what I'm going to be looking at here is a way to perhaps address some of the major issues with municipal solid waste. And here what we're going to be doing is we're going to be looking at doing municipal solid waste gasification followed by a hydrogen membrane so that we sequester the CO2-rich retentate stream that would contain all the heavy metals, so that the membrane is basically keeping all the, I'll call it the junk on one side, and all the valuable hydrogen would be going through the membrane. So to give you a feel, here I'm looking at a particular case of trying to, could we take the municipal solid waste from Allegheny County, which is basically the Pittsburgh region of Pennsylvania. It generates about 1.5 million short tons per year of municipal solid waste. The majority of it can actually be used. A lot of metals and glass and other components would have to be separated out. And myself and Paul Balla, who is co-author on this, estimated that there'd be total Exergy of about 400 megawatts if you could get all the useful work out of the combustion, the combustible parts of the municipal solid waste. And that's things like yard trimmings and food waste and wood, plastics, and cardboard. So we took based on some DOE and EPA studies, we tried to estimate what the municipal solid waste would look like. And here we show a breakdown of what weight percent is water, ash, and then carbon, hydrogen, oxygen, sulfur, and chlorine. And these were used as inputs into our system modeling. The main kind of equipment that's being added, because we're looking at here, how do you retrofit like a coal power plant that's let's say a coal power plant that is recently closed, and there's a number of them in the Pittsburgh region. Coal power plants that have closed because of environmental concerns. So what we're looking at, can we add a gasifier to generate the hydrogen and CO2? And so the gasifier chosen was a Mark IV Sasol-Lurgi dry ash moving bed gasifier. Right, so you're adding in feedstock at the top. It's a lock hopper, and then it's being pressurized and is being added into the gasification region. And then there basically a solid bed forms And then at the bottom there's a moving grinder that will take the ash out into the ash lock. And then steam and oxygen are being added at the bottom, and then the syngas will be generated and then condensed before eventually going to, well, it will be cooled before going to a water gas shift reactor. One thing to point out is we're adding lime into the gasifier to neutralize sulfides and chlorides that might be in the waste. We're not concerned too much with dioxins because there's an absence of oxygen, but still we're adding in the chlorine to make sure that we're not forming any dioxins, so that there's basically no chlorine or oxygen available. And so some of the advantages of this gasifier is that it's capable of handling the coarse size. It may be difficult to get municipal solid waste into the 100 micron size, which might be needed for a train flow gasifier, right? So we don't have to do too much pre-handling with this gasifier. And then this gasifier already has a rotating bed at the bottom, which prevents agglomeration. And I would say the main reason that we looked at this gasifier is that its countercurrent design makes it extremely efficient, which is extremely important for municipal solid waste that might have a fair amount of water. So the nice thing about this is that it's basically a countercurrent flow, so that you between the solid and gas there's always a fairly low temperature gradient, and you're able to basically cool the hot gas using the coal or using the municipal solid waste. Remember, there's no actual coal going into this, so anytime you see the word coal here, replace it with MSW. And then the ash, as it leaves the gasifier, is actually being used to heat up the steam and air that's entering in. So here's the overall process flow diagram. It's quite large, so I'm going to break it down into, here's the existing equipment, and the existing equipment is the Rankine cycle, and then we have an air heater, boiler, and then basically the boiler is going to heat up the steam in the Rankine cycle. Okay. And then this heat exchanger is this one down here is the air preheater, the hot side of the air preheater. This is the cold side. The other thing to note here is that everything up here is all the new equipment. Right, we're going to have a gasifier. We have to have an air separation unit to create the oxygen. We're also going to use that nitrogen to sweep a membrane. So we've got our gasifier, we got a water gas shift reactor, and then that's being that goes to this membrane unit. Hydrogen and water permeate through the membrane and then go to the boiler to be combusted. The hydrogen is combusted, and then the water just goes into the boiler. And then we have the retentate of this membrane is rich in CO2, in which case we compress out the CO2 and then we pump that for underground sequestration. And the thing to note here is that we are assuming, at least until we can prove, that contaminants like mercury would not go through the membrane. There have been, I'll talk about this membrane a little bit later, there has been testing on this membrane on sulfur species, but to my knowledge there has been no testing of lesser contaminants like mercury. So here these membranes are being modeled off of PBI membranes being developed by Los Alamos National Laboratory and Stanford Research Institute. And the goals here are to extract hydrogen from the syngas while keeping the pollutants on the retentate side. One nice thing is that ASU generates a fair amount of nitrogen, which can be used for sweeping these membranes. And the effect of that is to increase your driving force, so you can get more hydrogen through with less membrane. So here's what these membranes are turned into fibers, and then turned into bundles. The fiber, every fiber, there's going to be a porous section and then a dense coating on top of it. And here for this model at least, we're assuming the following permeabilities. You can see water vapor is the highest permeability, followed by hydrogen, then CO2, and then carbon monoxide and nitrogen are about 100 times less than hydrogen. And just as a reminder, so we're assuming that there's an existing power plant with a working Rankine cycle, and we're just going to be adding to that. So what we did was, first thing we did was some thermodynamic modeling, basically a first and second law, or i.e. when you combine first and second law, you get the Exergy law, or Exergy Analysis. And what we did find was that of the 400 megawatts of Exergy originally in the municipal solid waste, we were generating about 71 megawatts of power. It's not particularly a high number. That's only 18% of the original Exergy. So we wanted to show a breakdown of where the Exergy destruction is occurring in the plant. And one of the major components is the gasifier. This gasifier, even though I said it's compared to train flow, it doesn't use much oxygen. Still a fair amount of oxygen is being consumed in that gasifier, which destroys about 20% of the Exergy. Water gas shift is not a large Exergy destruction. The hydrogen membrane is fairly high. I do want to point out that part of the reason it's high is that we purposely, at least here, we're using very, very large driving forces to get a lot of hydrogen with very little. This Exergy destruction may not be indicative of the Exergy destruction if your permeate side were at higher pressure. The next thing I want to point out is the ASU had both a power, there was a power cost, and there was Exergy destruction associated with it. Now the CO2 condensation and compression had some power. There were some pumps, and then there was also some Exergy destruction associated with that subsystem. The air preheater had some Exergy destruction. The largest source of Exergy destruction was actually the combustion and then heat transfer to the Rankine cycle. That's where most of the Exergy is being destroyed. Here in our model, only a small amount of Exergy is being destroyed as the flue gas goes out to the environment. That's like a 5%. The Rankine pump, while it consumes some power, has virtually no Exergy destruction. And then our Rankine turbines, that's where we're generating most of our power, and there isn't much Exergy destruction going on there. And then we have a closed feed water heater, only a small amount of Exergy destruction, and the Rankine condenser to the outside environment only destroys about 4%. So in sum, we have about 18%. It's not a particularly high. You probably, if you were designing something from a green field, you could probably easily get in the 30s, maybe getting up to the 40 range. But the point here is that there are existing power plants across the U.S. that are being closed, and perhaps they could be used to generate electricity from municipal solid waste. So ultimately, what we care about is going to be our return on investment. So I'm going to walk you through the financial analysis. We assumed that to do all these modifications to the power plant would take 3 years. After those 3 years, it's operating for an additional 30 years. We assume the capacity factor is 90%, which is higher than the higher capacity factor than I've used in other models, and that's particularly because this power plant, because it's getting a tipping fee, is actually going to be wanting to operate at really high efficiency, at capacity factors. It's, as we'll see, especially if there's CO2 sales, the electricity sales is not necessarily, meaning even at the electricity sale price is low, it still may make sense for this to operate. So that's why that capacity factor is high. And then we're going to be looking at tipping fees varying from $10 to $50 per short ton of municipal solid waste. We're going to be looking at CO2 sales from -10 to $20 per ton of short per short ton of CO2. One thing we're keeping constant is the electricity revenue. That would be a separate analysis, but for here we kept it constant at $50 per megawatt hour, which is around kind of an average electricity sale price from power plants, not what you pay as consumer, but what you pay the power plant would receive. And then we used that cost of lime, which is being used to capture some stuff, some acid gases. We have an assumed cost for the PBI membranes, which is both the cost, the total would be for the membrane and the reactor unit, pressurized reactor unit. We're assuming $900 per meter squared of membrane. And then we're at least we're not looking at the replacing. We did not include a cost to replace the membranes, which would probably be that 300. The reactor probably would not need to be replaced, but the membranes itself might. But we did not look at that right now. So here I want to just give a summary of the capital costs. You can see gasifier and water gas shift are some of the major costs. Our ASU is another major cost. The membranes were not, they were sizable but not large compared to some of the other costs. And then we had some small estimates. We had some estimates for the upgrades to the existing equipment. This is not to replace the existing Rankine cycles, but just some kind of upgrades. And then we had we took all the capital costs and then we multiplied, we assumed that the actual installation was going to be equal to the equipment cost, so that you can see our total capital costs were assumed to be 2 times the raw equipment costs. And this is because we're assuming a brown field, that we don't have to buy the land, or we don't have to start from scratch. This is an existing site where we just have to add in some new equipment. And then we estimate our recurring costs. And here, these recurring costs are for the mid case, what I'll call the mid case. And that mid case was when you had a $35 per ton of municipal solid waste. That was in the middle of that range. In that case, you'd be getting about $29 million per year in tipping fees, which was about equal to the electricity sale price. And then here we took the mid case of being $0 per ton of CO2 So we're not getting any electricity sales. What we're assuming is that someone will take the CO2, but they're not charging us, and we're not charging them. And then in the lime, we're assuming a cost for the lime, we're assuming a cost for cooling water, and then we're assuming a cost for operating and maintenance. And in total, after your positives and your negatives, we're finding that we're at least generating revenue each year. And you could see it would take us over 10 years to pay back if there was no interest. But, of course, what we're interested in is solving for the IRR, the internal rate of return on investment. And so the IRR was calculated assuming a $50 per megawatt hour electricity sales and all the other sales as shown above. And we determined that the real, so inflation adjusted IRR was 5.2% per year. So that's what would be your profits on investing in this project. If all these assumptions were true, that'd be your real return on investment. So after inflation, after adjusting for inflation. We also looked at what the levelized cost of electricity would have, how much your sale price of electricity would have to be if you had to give a real interest rate of 6% per year. And you can see that levelized cost of electricity is about $52 per megawatt hour. So what we're finding is in this mid case, we're kind of right in that range in which this is like potentially interesting. Like these, we're not like so high that we should be going out and doing this immediately, but they're not so low that this should be just kind of thrown out as a bad idea. So the next thing I want to look at is we also looked at varying two of the many two of the many assumptions, right? The tipping fee is not $35 per ton everywhere. You know, it could be anywhere from like 10 to 50. And then the other thing that we varied was the CO2 sale price, because in some locations in the U.S. you'd actually have to pay to sequester it underground, which might be on the order of $10 per ton of CO2. Whereas if you happen to live in Texas or Alberta, you could actually sell it right now for $20 per ton of CO2. So this graph here is showing the inflation-adjusted real rate of return on investment, and one thing we are keeping fixed is the sale price of electricity at $50 per megawatt hour. So you can see we're getting, depending on what your assumptions are, you can get anywhere from 0 to 12% return on investments. The interesting thing to point out is that there's many different places in the U.S. where this might be potentially interesting, all of which were yielding about an IRR around 6%. When we just kind of some rough estimates, there's going to be locations in the U.S. Where the tipping fee is very high, like New York City, where it's going to be on the order or greater than $50 per ton of CO2. But you're likely going to have to pay to sequester the CO2. There may be some places like Pittsburgh where the tipping fee is maybe in the middle range, but there may be companies in this region that may take the CO2, perhaps take it to sequester it in Marcellus shale wells, right? But there's already existing wells. We may not have to actually pay to sequester the CO2. And then there's actually places in Texas or Alberta where they are paying you, on the order of $20 per ton of CO2, but the tipping fee for MSW is not very high. So I just wanted to point out that, you could be anywhere kind of on this graph, but three potentially interesting places, all are kind of yielding this kind of around 5 to 6% return on investment. So I want to thank Paul Ball, my co-author, Paul Balla, as well as other people who have helped in the development of these models, such as Sweta Agrawal, Brian Chang, and thank funding from the NETL Strategic Center for Coal. I do want to point out the views in this presentation represent the views of the authors and may not reflect the views of the Department of Energy. So I thank you for your time.